For me, it's a pleasure to introduce Leila Postasio. She is a SIIM professor in the Department of System and Computer Engineer at Harvard University, Canada. It's a pleasure for me because Leila was my student in a master's degree here in Brazil in the program of Physics Applied Medicine Biology. Was also a student in the medical physics program, so that was a pleasure for me. And she obtained her doctorate in 2015 in biomedical engineering program at the University of Manitoba, and since 2020 is assistant professor at the Harvard University. The area is spectroscopy, microscopy, optical microscopy, 3D bioprinting, and other tissue engineer, and with emphasis in understanding fibrosis, chronic disease, and today it is here to talk about Pandora box into bioprinting. Thank you, Leila.
Oh, it's my pleasure. Thank you, Luciano, for the kind introduction. I wish I was there in person, but unfortunately it didn't work this time. So hello, everyone. Good morning. And yeah, so Luciano kindly introduced me a little bit, but from this short slide, I can tell you that my trajectory has been a little bit all over the place, from medical physics to engineering, and now a little bit in medicine. And the story I would like to share today is about the combination of different areas. So as you can see, as you can imagine, tissue engineering has a lot of different integrations between biology, of course, engineering, physics, and so on. And today I will focus more on the technologies related to 3D bioprinting. So probably many of you are familiar to some extent to it, maybe not. So I will give you a very overview of the different techniques that we have to generate artificial tissues for different applications per se. And this first slide here, I would like to bring your attention to basically the differences that you can see between the two pictures, right? On the left, we have what's called a 2D cell culture. So that's when we have cells growing in a petri dish. They basically move around in the plane there. And once you allow them to have a little more freedom, you have them in what we call 3D environments. So you have a collagen gel, you have some sort of substrate where the cells can move in more than one direction. They start to form interesting structures. So instead of having them kind of side by side and growing as a film, they become a little bit of clusters. Depending on the type of the cells, the structure that we have there is going to be a little different. And that's because partially of the idea that, of course, if the cells are growing in a petri dish, they can only do so much. They will have limitations in terms of where they can attach, where they can go, what kind of perceptions they can have from the environment. The communication between the cells is going to be a little different than when you have them, again, in a certain substrate with a little more material in there, where they can move at least in X, Y, Z a little bit, and you have an extracellular matrix, you have a little bit of a environment for them to move around. That has been called 3D cell cultures up to relatively recently, but today in the area we call these little ways to grow cells as 2.5D cultures. And that's because 3D bioprinting came to the picture. So now we call cells growing in a petri dish a 2D. When we have a little bit of a substrate, that becomes the 2.5. But when we are printing actually complex structures, that's what is going to be the real 3D. Okay, sorry, I was just hearing, I guess, myself in the room and it was giving me a little bit of echo. Okay, so do you still have me there? Am I still there? Could you please confirm on the chat? Hello? Okay, sorry. You disappeared from my screen. Okay. Okay, so there are many advantages of having cells and having experiments done in this 3D environment. So I won't read all of those, but basically the main advantage is we are going to mimic what's happening inside of the body a little better when we have the cells and the environment placed in 3D. So I would like to then today chat with you about from where this idea came from, right? From where this interesting approach of printing, 3D printing organs and tissues came. And this started not recently. That started actually in the 80s when some people started developing the idea of 3D printing, not bioprinting yet, but printing. And in the 80s, there was a lot of development in terms of getting this technology ready to deal with different types of materials, dealing with different types of formats and shapes. One of the milestones was achieved by Charles Hall, and he is considered the father of 3D bioprinting. So here we have a picture of the very first 3D printer. And as you can see, just by looking at the screen and the type of equipment, you can tell it's from the 80s. And so here's a picture of Chuck and one of the massive constructs that he achieved by using this new technology. So they had this technology patented, and that basically opened the doors to developing other approaches in terms of creating these 3D structures. At this point, we were still dealing with plastics, some sort of artificial filaments. We were not doing anything biological yet. And this is my video is not going to, oh, no, none of my videos are going to play because I had to export this as a PDF. But here is an example of the very first commercialized 3D printing technology. So basically the idea is you will have some sort of a polymer in there, and then you have laser light curating this polymer or making it become harder. So the video was going to show the laser light going around, and this polymer here was going to come up. And as the laser goes around, it would make this structure here harder. So that was the very first 3D printing technology that came to life in terms of commercial applications and so on. So that was all very cool, very interesting. But then things, of course, they didn't stop there. So in the 90s and early 2000s, sorry, there was a lot of progress made in both the 3D printing world and then the 3D bioprinting. It started to come to life. And that was mostly thanks to the prices of this technology come down significantly. Back then in the 80s, the basic 3D printer was going out for about $10,000, which was a lot of money at that time. And then all of a sudden, the technology and some improvements allowed the system to become much cheaper, like costing around $1,000 instead. So that again opened the door to another burst in development of this technology. That was more or less around the time that we had the biological system to start being printed. So here we have a picture of Dr. Anthony Atala, and his lab, his colleagues, they were among the first ones to actually incorporate this idea of 3D printing into biological tissues. So before the 3D printing boom, they were already manufacturing artificial tissues, as they call, by hand. So they would physically take some proteins, place cells in different places, and kind of build the structure that they needed to build. They were specialized in bladder diseases and bladder tissues. So they were really good already doing it manually per se. But when the technology of 3D printing came around, they were among the pioneers using and adapting that to biological materials. So they, of course, they started printing bladders artificially using the technology. And it's funny because here there is a quote from him. And he says that manually, it was very interesting because they had more control overall of where they would place things and how they would arrange things. But the 3D printing technology allowed them to produce things in scale. So everything was allowed to be much faster and much more efficient. And that started another chapter in our journey of the 3D printing. So again, around the 2010s, 15, 20s, a lot of things happened again. Around 2015, CellLink, which is one of the major manufacturers of 3D bioprinters, they came to life and they started diffusing this technology even further in laboratories. So at that time, there was a big boom in the bioprinting road. And the CellLink has been one of the pioneers. Now we have, I don't know, over 200 manufacturers producing bioprinters in a format or another. And again, that triggered another boom in research and technology development. So putting them side by side, we can see we came a long way when we compare the very first 3D printer from 1983 with the CellLink one that has been sold, for example, now in 2022, 23. So the technology for sure changed a lot. The bioprinter, as you will see, we have quite a few different specifications compared to the regular 3D printer. But in essence, in terms of the basic way that it operates, it's very similar to the 3D printing. I like to say that instead of using the filaments and the plastics, you just put cells and proteins, and then it's basically very similar what happens in there. You have to control temperature, you have to control several parameters, but that's in essence, that's how it works. And unfortunately, I cannot see you, so I don't think that's going to work really well. But I wanted to ask you just to take a pause here and think about in how many ways do you think we can prepare potatoes? And unfortunately, I won't spend too much time here because I cannot see you, but think about it, like thinking in your mind how many ways you can think of making potatoes, right? So when you're at home, you want to make a dish, how would you prepare them? Okay, so we can for sure, very straightforward, we can, for example, get potatoes, slice them, make some casseroles or something like that. Another way to prepare them is by shredding the potatoes. We could dice them as well, make some nice cubes. Or we could, for example, mash the potatoes as well. So, of course, there are many other ways to prepare them, but let's just say that those would be the most obvious choices for most of us. And what's interesting is the same way we prepare potatoes, we can think about 3D bioprinting materials. So there are different ways that we can prepare or construct dishes, and they all are going to be around this idea of slicing, shredding, dicing, or mashing. So I'm going to briefly show you how each one of those work and link them to, again, like my video is not playing unfortunately, but this arm here would have a specific polymer, and this would move up. And here we have a solution, again, similar to the one that I showed you before. We would have laser, and that would start curating the material. So here is a dish. It would have the kind of in liquid form polymer. This arm would move up, and then as it moved up, the shape or whatever you're trying to print would appear. So that was one of the approaches that we can use in 3D bioprinting. So that one is called digital light processing. Again, we have a light source here. We have the polymer in there, and that's how we are going to be creating the shapes. Here I have an example showing how it would work with biological components. So here is a hydrogel that has been printed in that way. And of course, you can be creative. You can play and do all kinds of forms and shapes. In this case, specifically, this group, they were having a layer, in this case, for example, skin or muscle in between the polymer or the structure that they were trying to print and the laser. So that was to attempt to do an in vivo 3D bioprinting. So instead of having something like printing something and then placing it whatever they wanted, they actually printed within the tissues. And here are some examples showing how the structures would change if they have, for example, nothing in between. Of course, we have perfect contours, perfect structure. But if we have a layer of skin, for example, on top, we still can distinguish the donut shape, but it's a little more less centered. And the same with the muscle. The muscle is a little thicker band, so therefore the laser would not penetrate as much, but we still can polymerize the material that we had in there. So that was one way, and that technology is not that common anymore. So that was something that was interesting in the beginning, but now the vast majority of the labs, they have moved away from these 3D bioprinting technology, and a lot of the labs now rely on extrusion and some other approaches. Extrusion, if you look around most of the printers, that's the main principle they work. And that would be probably the most applied or the most used technology in tissue engineering labs. So basically, when we talk about extrusion printing, just thinking about squeezing a ketchup bottle. So it's basically the way it works. We will have the polymer inside of a container, a reservoir, and then we will apply some pressure, and then the content is going to be extruded towards the region that we want. There are some limitations with this technology, and one is related to lower cell viability, and I'm going to talk about that a little bit. But basically, imagine you have to squish the cells out of the syringe, out of the reservoir, and therefore you're applying a lot of shear stress on those cells. They are not going to be happy, and therefore the chances are you will have high cell mortality in that case. Generally speaking, this technology came a long way, but generally speaking, it's among of the ones with the lowest resolution, because again, try to make some interesting patterns squeezing a ketchup bottle, right? So you can only do so much, depending on the size of the structure that you are trying to print. You are not going to have too much control, but if you are trying to print something that's big enough, then it should be okay. And generally, it's kind of slow because you have to physically move your ketchup bottle all over the place in order to create the structure that you want to create. And generally, it's better for when you are trying to create large 3D structures. And yeah, so when you do extrusion, of course, there are lots of ways to squeeze the ketchup out. So the materials. So one of them, the most common one, is the pneumatic approach. So basically, you have pressure, and then you press the bioink down, and then you have your pattern being formed. There is another one, relatively common as well, that's based on a piston. So imagine that you have a syringe. You just have something that's going to press down your bioinks or your materials. And then this one is not that common, but sometimes there is this screw-like mechanism. So this one is basically going to go around and around, and then all the material is going to be extruded. You have an inlet that you can connect to have a continuous flow of your materials. So again, as you're probably noticing, every single step, every single part related to bioprinting and tissue engineering in general, you can open a few extra doors as you move along. So you have the option of choosing what type of bioprinting you want to use. Within that type, you have a choice of what kind of extrusion method you want to use, etc., etc. So this is a picture of how the extrusion printer generally looks. So you have, for example, reservoirs. In this case here, there are only 2, but some printers, they have 4, 6, and so on. Each one of those reservoirs will have a different type of biomaterial or different type of cells. Usually, you will have a combination of 1 or 2 types of cells, and then, for example, collagen in one, elastin in another one, some sort of gelatin to give some structure. And of course, you have the printing stage. Sometimes the head moves, sometimes the stage moves, depends on the printer. But in general, that's how a typical extrusion printer will look like. We can, again, print very nice and large structures, so that's great for those applications. As you can see, we can notice the squares here, the holes in there with the materials, and then, of course, we want to see how the cells are behaving. We can take advantage of microscopy and imaging to look what's going on after we print those materials. And again, this is one of the most common approaches, but sometimes we can take advantage of a different technology for printing. And this one is what's called the inkjet printing. So basically, like our old and regular printer that we all had at home at some point, it's going to work very similarly. So we have a layer of bioink that's being accumulated within a certain platform, or in this case, it should be the paper, but for us, it's going to be something else. And the limitations of these modalities related to, we only can work with low viscosity biomaterials. That's not always the best option for us, depending on the application, depending on the type of cell. We have to wait for the bioink ink to solidify, just like, for example, when you print photography, I don't know these days anymore, but usually we had to wait a little bit until the ink would dry off. Otherwise, you would make a mess of your picture. But this is kind of similar. You have the bioink layered in the platform, and then you have to wait a little bit until everything is in place. You cannot work with too high density of cells because, again, the whole mechanism and the whole stress process that you make the cells suffer, it's not going to allow you to have too high densities in there. The best application is mostly related to speed. So you can print relatively large areas relatively quick, and it has been used a lot to create skin grafts. So sometimes you have to just create a layer of tissue, and you don't need too many cells. You just have to have something kind of a bandage to cover a wound or something. So the inkjet is your best choice. And the way it works, again, it's slightly different than the others. But for example, we could use some thermal treatments to allow the bioink to flow. So you will have a little heater near the nozzle here, and your bioink would flow, get heated, change the viscosity to allow it to flow a little better, and then be deposited within the film. Another approach is with piezoelectric actuators. So that would control the flow a little bit, and then that's what would give you the control over the bioink, where it's going to go deposited. This is an example of how something printed with the inkjet technology would look like. So you do have some freedom to do a little bit of patterning. You can layer, for example, different things on top of each other. Again, keeping in mind that the viscosity of these materials will have to be within a certain range, because otherwise they will get mixed up, for example. But overall, you can get some nice patterning, nice structures in there. So here are some examples of, for example, writing the letters, the acronym for this lab, or also in this case here, they had concentric circles being printed with different materials. So green was something, and the blue was a different one. You do have some control. It's not perfect, but it does a very decent job considering how fast you can print those structures. And the last but not least, the mashed potato one, or the laser-assisted technology, is basically imagine that you are just placing a bunch of these little polka dots on a dress to create some sort of pattern. That's how this last major type of bioprinting works. And the limitation here is going to be the printing speed, because of course, imagine that you have to place droplets all over the place to create whatever you are trying to create. It's more complicated to print multiple layers. So this one is one of the biggest limitations of this laser-assisted one. And it tends to be quite wasteful, because as you start placing the dots and so on, not necessarily you are going to be placing them in the best locations. You might have a little bit of trouble creating your patterns. Quite often you have to use way more material than you normally would with the other ones. The best application for this one is related to having the control to place the cells exactly where you would like to in solid constructs. So imagine that you have already something like some structure, and that you just want to have certain cells placed on top, at the bottom, on the side, and so on. So this one will allow you to have this control to go around and have the cells placed where they should be. And this is relatively simple compared to the other technologies. So basically you will need, of course, a laser, and that's going to be a few layers in there. Some is going to be what's called the energy absorbing layer, and your bioink is going to be down there. As the laser moves around, it's going to, imagine that you have a kind of a wax layer in here, and then as the laser goes around, you kind of melt the wax, and it starts dripping where you would like it to drip. So that's kind of more or less how it works. Here, again, just an example to illustrate how this type of bioprinting works. You would have a construct, for example, something like this, to mimic bones or to mimic something that's a little more solid. And then you wanted to have specific type of cells placed in certain locations of this bone structure. So in this image here, and again, probably you're noticing microscopy is your best friend in 3D bioprinting, and because of course we want to see where things are or what's happening there. And the blue lines here represent this construct, and then you have the cells placed in green around some regions that you wanted to have. So you can be creative, you can create some interesting structures. So this one is to mimic a trabecular bone. And then the same thing, you wanted to place certain types of cells in certain regions of this structure. Here we have, for example, cardiomyocytes aligned. So for muscle tissue, you want them to be all organized, all aligned, so you can create some sort of a grading and then have these cells placed in specific locations to have that pattern happening there. And yeah, from the 80s until very recently, 2018, so there has been a lot of things going on the bioprinting world. So things that started quite simple, just trying to print what we call scaffolds. And we started playing with different types of cells, different types of biomaterials. But I would like to bring your attention to a very interesting milestone, per se, that happened in 2018. So a group from Tel Aviv University, they were the first ones to develop and use the technology that they call FRESH. So this one has been one of the most powerful ones to actually mimic complex structures. We are not talking about printing just layers of things, but now trying to create mini organs, completely functional, and so on. So in case you are interested in reading more about this is the full paper, if you would like to take a look. So that was published in Advanced Science. It's one of the main journals in the field. Quite often, if you go there every other day, there is something cool being published there. But that was one of the milestones in terms of development of this technology. And basically, in a nutshell, what they did, they wanted to create a heart-like structure with all the ventricles, all the chambers and everything. And they extracted the whole process this is oversimplifying things, but the whole process started with mapping the structures that they needed. They had to create the ideal hydrogel or the ideal biomaterials for creating the structure. They came up with the bioink formulations that would be okay and allow those specific types of cells that should live in the heart to live. They had to use certain technologies related to 3D bioprinting. And then, of course, they eventually created a mini heart. So I'm not going to go into all the details. Again, if you would like to read this paper, I fully recommend, but I'm just going to walk you through the main figures so you can appreciate how amazing has been this research. So they took a little bit of tissue, and from this tissue, they isolated some stromal cells this is basically fat tissue. So they extracted the cells, and they were left with the SIIM, or the extracellular matrix. So all these proteins here, they eventually got transformed, quote unquote, as in a bioink. So you can do some chemical processes where you can transform this carcass of the tissue into some sort of a gel. And from this gel, you then can use it as a basis for bioprinting whatever you want. In this case, of course, they wanted to have a heart. So they isolated all this ECM. They had all the proteins that they would find in the body available to them in this gel form. And then from there, they had the freedom to use that as a basis to print something. So those images here are just showing that the cells eventually survived. They managed to differentiate them into cardiac cells. And the next step was they wanted to print a heart. So they needed to know how a heart looks like in terms of design. So the first step was to perform a CT scan of the heart to map where the blood vessels were. They also did some mapping of the chambers and the tissue walls. And they created a kind of a CAD model. So they mapped off all the arteries in this case here. So they created this CAD model. And they used the bioink they extracted from the tissue. And then they started printing things that would resemble those vessels. Here we have some images showing the sarcomeric actin. So those are the cytoskeleton proteins of the cells. And in the red is the kind of the structure that they were trying to create, like the vessels, for example. And in blue is just a bunch of nuclei of the cells. If we zoom in this area here, we can see that there is a little bit of a kind of a branching and tube-like structure being formed. So they started printing those things. In this time, it was not just printing it by itself, but they were the first ones to use what's called support material. So basically, you have a kind of a gelatin, a gel in there that serves as a basis to allow your 3D bioprinted structure to be held in place. If you don't use in this case, if you don't use the support medium, everything will just collapse or get mixed up. But using the support medium, you can promote the structure to be preserved, and then you can be a little more creative with your shapes and formats. As you can see, there is quite a bit of complex pattern here in the purple image. And yeah, so that was a very long story, but they eventually managed to print all these vessels, all the structures, using the support material. As you can see here, they managed to create a mini heart. So they had all the vessels structures, they had kind of the walls of the heart in there, all with different types of biomaterials. And that became a very interesting proof of concept that, yes, it is possible to print all these kind of crazy, complex elements or objects. And here we have an imaging of this mini heart. And as you can see, we can notice quite nicely in orange the vessel structure. And then in purple, of course, the wall and the overall general shape of the heart. So you can see some chambers in there, like the ventricles and what should be the atrium. Here are images of the cells showing that they are alive, they are happy living there. So it was basically a success. And up to now, basically, I told you about this step here, which is called the processing step, which is when we decide what kind of 3D bioprinter we might need to use for our application. However, this is just one step in a very complex pipeline that involves the tissue engineering domain or the 3D printing domain. So there are quite a few things that we have to take into consideration before and after printing, and I will just walk through a few of them. So let's open the Pandora box, because up to now was the easy part. It was just one step, but let's take a look briefly what happens in each one of those. So in the first one, we have to do some very critical choices before we get to the point that we are ready to print. So the first one, of course, is selecting what kind of cells you are going to be printing and decide on how you're going to evaluate their viability, meaning how you're going to assess if they are alive or not. And there are quite a few ways that you can test viability. You can selecting cells, of course, is going to depend on your application, but looking at viability can be done in a few ways. One of them, the most simple and widely used one, is based on microscopy. So we can basically label the cells with specific fluorescent labels, and then we can look how many, for example, show up in green, how many will show up in red, and those are going to be attaching depending if the cell is alive or if the cell is dead. Of course, you want to have as close as possible to 100% viability. It never happens. Usually anywhere between 75-ish, 80%, it's considered a very good number for cell viability. Then, of course, you have to select your biomaterial. Once you know what kind of cell, what kind of construct you are going to be working with, you'll have to define what's going to be the basis of your printed construct. And guess what? What's easier to print is not the best for the cells. And what's best for the cells, it doesn't hold structure very well. So this is just a summary of the decisions or the considerations you have to make. Because depending on, for example, how the polymer is, what's the concentration, how cross-linked the polymer is, that's going to affect the stiffness of your material. And some cells won't do well there. And printability and the shape flexibility, of course, the harder the material, the easier it is for you to have the shape hold. But again, that's not what the cells like most of the time. The biocompatibility is going to be better with less stiff materials, but again, we have to find a fine balance somewhere in the middle where we can allow the cells to survive generally okay, but at the same time allow us to have some sort of control over the shapes and over the printability and how to maintain this structure. So this is the constant battle in the pre-processing phase, defining the biomaterials, defining the formulations, defining the cells, and then moving to the next step. In terms of the biomaterial selection, there is a lot of extra considerations that we can make. One of them, for example, is related to the cross-linking. So printability, of course, is a big factor. Like I said, you want to have something that's going to hold structure. You don't want something that's too liquid or something that's completely hard. You have to find the happy medium in there. So analyzing the mechanics of the hydrogel is important. The biocompatibility, of course, is going to be to some extent depending on the cell type that you are going to be using. And the cross-linking, which is basically a way for you to manipulate how hard those materials might be, it's another can of worms. So those are just examples of the three major collagen-based hydrogels or bioinks. And usually we mix either alginate or gelma or gelatin with something else. And each one of them have their unique properties. And you can fine-tune a little bit the cross-linking of each one of them. How you do it, this is listed here in the box. As you can see, there are lots of options and lots of approaches that we can take to do this selection and to make this decision. In the planning phase, you also want to start thinking about the morphological design. So what kind of organ or tissue or structure that you're planning to print, how you're going to find a way to basically create a blueprint of this structure. From there, you have to create your CAD model, because this is what's going to be sent to the bioprinter. It doesn't matter what type of bioprinter you are using, but you always have to provide some guidance in terms of what kind of pattern you want to see in there. It can be as complex as a mini heart, or it can be just, for example, like a little ring. So morphological design, if you want to layer materials, or if you're going to be working with just one material, that's another decision that you have to make. And if you're going to have patterns, gradients, and so on. The biomaterial selection, there is a lot of physics involved in there. So you have to be aware of all the materials and the rheology properties of these materials. So how viscous it is, what's the pressure that you're going to need for doing this. If it is extrusion, for example, how much you're going to be pressing them. That's going to go back to cell viability. What's the maximum you can press your material without compromising the cells and so on. After we printed, which we know all about by now, we have to do some post-processing, right? So we printed our construct, and we have to do something with it. We cannot just leave it there in the printer. And because we are talking about bioprinting, we do have cells, we do have live entities in there. So we have to bring them and to let them grow or to let them curate or whatever we need to do. So quite often we have to do more tests in terms of after printing, after doing everything, how the gel is holding up, right? So how the structure is holding up. Is that absorbing up water? Is that being swelling? Is that suffering some degradation, meaning that the cells, for some reason, they didn't like the environment. So therefore, they are not forming the structure that they should be forming. So all of these can be evaluated after the printing. And we can use another collection of techniques for doing that. There's some biological assays, again, like you can label cells and look for specific cues of how they are doing, or you can look at the material itself. You can use, for example, atomic force microscopy, where you can look at how stiff your surface is, how stiff even the cells are within that material. So all of these you can do after the printing, and that's something that you will usually use this information to guide you for the next batch of experiments, because quite often you start somewhere, and of course, it's not going to be perfect in the first batch. So then you do these tests, you do these evaluations, and then you move forward to the next phase. Talking about evaluation, we can do many, again, I won't go into the details at all, but there are quite a few ways that we can evaluate, again, based on taking advantage of microscopy, so we can see what's going on there. We can play a little bit, changing the materials, changing the patterning, changing the amount of cells, all these kind of things. We can change how we are layering the structures. We can decide if we are going to be using what's called a bioreactor or not, which means can we have continuous flow of nutrients for this printed construct, or we are just going to leave it in an incubator and let it grow. So all these decisions can be evaluated, and that can be a very important step in terms of defining what are going to be the next phases for you to build your construct. So if we were to summarize in one slide what's going on, that's basically a kind of a mind map of 3D bioprinting, tissue engineering slash creating artificial organs and tissues. So of course, we start somewhere from some sort of cells or tissues, be that from animals or humans. Quite often you need to do some imaging, again, to define your pattern or even to see how things are going on. You have to spend some time culturing the cells and tissues. You have to define your bioinks, biomaterials, the type of bioprinting approach that you're going to be using, and then evaluate and start over and over again. There are some challenges with the bioprinting technology. It's, of course, although it's super powerful, it's not perfect yet. It's far from that. And a few of the main challenges that we have these days is related to vascularization, meaning that when we print those constructs, they are not going to be vascularized. So you print, for example, a nice wall or a nice ball of something, but not necessarily you will have the blood vessels providing nutrients to every single layer of these tissues. So that's a very active line of research now to incorporate vasculature into these printed constructs. Immune rejection, sometimes it happens because you have to mix and match biomaterials with cells and so on. So sometimes it's a little bit complicated to find what's the optimum combination between something that you can print versus something that the cells like. And that goes hand in hand with the biocompatibility, right? So quite often, again, like the ideal things for printing are not what the cells like. And that's when you start to try to negotiate your way in finding the happy medium in there. And just to end, I would like to share a little bit of the research that we do at Carleton with the Team Hub group, so the Tissue Engineering and Applied Materials. It's a group that I have been leading for the past few years with a few people. So those are some of the principal investigators related to the Team Hub. And we are a group of people involved from different departments from Carleton and also from different institutes in Ottawa. And we do, of course, take advantage of having imaging toys in there. So as Luciano kindly said, most of my background is in imaging and image processing. So yes, I love having microscopes in there. So we do have some super resolution microscopes. We have spectrometers where we can look at the biochemical signature of these tissues. There are some people in physics working with custom build microscopes in there, which are amazing. We do have some technology for controlling the environments and, for example, exposing cells and tissues to hypoxia or lack of oxygen and see what happens when we do that. There are some equipment related to monitoring real-time cells. So basically you can leave the cells or the bioprinted constructs in there and we can set up things to take pictures every, 10 minutes and see how things are going. And of course, we do have a bioprinter, which is a microfluidics-based 3D bioprinter. Unfortunately, my video won't play, but I had a nice video showing how it works. I will try to explain briefly here, but as we call it the Medusa, because all the tubes connected to that, but we have basically those two main tubes plus the 4 with biomaterials. And we do have a print head that's actually a microfluidics device. So basically we are playing with the flow of these liquids in a very, very tiny volume and controlling how they interact with each other. And with that, we have a little more control over for example, the gradients, and we can reduce the shear stress on the cells. We have them surviving a little better this process of being printed. And yeah, so this is my video, but unfortunately it's not gonna play. And just briefly, one of the main researches that my group does there, it's related to understanding the extracellular matrix structure, especially in respiratory diseases. So the SIIM is a network of proteins. And if you think about many diseases that we have out there, in a way or another, ECM changes is going to be behind that. And in asthma, for example, which is one of the main topics that we work on, we can see that just looking at this picture here, we can compare how a cross-section of an airway from a normal person versus someone asthmatic looks like. Without knowing anything, it's quite obvious that there are quite a bit of changes in there. And if you look at this bluish, kind of greenish materials accumulated within the airway wall, that's collagen. So that's a fibrosis response. So if you heard about fibrosis, that's basically what happens in many tissues of the body. You have a lot of collagen accumulated, not in the right places. And that's one of the things that we are trying to understand. So what's happening to the tissues when we have fibrosis happening? One of the cells or the main suspects is a cell called fibroblasts. So they are the ones who actually make collagen and they repair tissues in our body. And those cells, they live happily in there until they get stimulated. And this stimuli can happen in the chemical or the mechanical form. When they are stimulated, they get activated and they started producing collagen a lot. And quite often, usually they should produce collagen enough to repair the injury. But when we are talking about diseases from asthma to cancer to cardiovascular diseases, they will go a little bit crazy and kind of overproduce collagen and create a scar tissue. And again, create some mechanical changes in the tissue that's going to trigger more of them to be activated and so on. So there is a little question happening in the field, which we joke that's the $1 million question. Usually when you have this fibrosis happening, this collagen accumulated, that's going to cause some inflammation within the tissue. But the inflammation by itself can be a trigger of having these fibroblasts being stimulated again to make more collagen. So we have a little bit of what comes first here, chicken or the egg situation. Because fibrosis is causing inflammation, but inflammation is causing fibrosis. So therefore, in terms of developing new therapies, we are not sure about what should be the target. Should we try to kill the inflammation to then address the fibrosis, or we should be looking at preventing the fibrosis to form and then reduce the inflammation. Of course, taking advantage of imaging and 2D, 2.5D, and 3D bioprinting, we are looking at developing artificial models of airways to look at the details of these basic mechanisms of fibroblasts and other cells. So here's just an example of a collagen gel. It's very hard to see probably, but we can see the cells in there contracting this gel. So here is a beautiful microscopy image of 2 fibroblasts, and the blue stuff is the collagen that has been produced by them. And one of the questions in terms of bioprinting is, can we actually create a synthetic ECM where the fibroblasts will display a behavior that's similar to what we see in vivo? And from there, we can start making adaptations and try to mimic, for example, an environment that's going to be similar to what we have in asthma, what we have in cancer, and so on. So of course, we are using 3D bioprinting to create these models. This is a funny story, but basically we call this model a sandwich. And we have the story started with the blue circle here, the ring, was with some cells, smooth muscle cells, and their job in the airways is to contract. When we started printing just the blue ring, it was very nice, beautiful, it looked really cool. We left it to grow for a few days, and then guess what? These cells, their main job is to contract, so they ended up contracting our ring. So instead of having this ring structure, we started seeing they would collapse and become a little blob of something. So long story short, one of the solutions, for example, thinking about design, was to have these red parts here, or assisted materials, to provide some support to the blue part and not allow these cells to contract the ring and become a blob. So this was, again, making a long story short, this was a strategy in terms of how to adapt the design to have our bioprinted construct to stay the way we wanted them to stay. And here's just a quick example, a very nice image showing how, by playing with the composition of your bioinks, you might be changing the structure of your constructs. So for example, if you play with the proportion between collagen and fibronectin, just by looking at the images, it's very clear to see we have more or less control over the structure that's being formed. So in this case here in the middle, it's a disaster, so we don't have the ring anymore. On the right, it's kind of looking a little better than the left one. And currently, unfortunately, this was supposed to be an animation, so it's covering up what's underneath. But right now we are at the phase that we are printing hollow tubes. So we moved away from the rings. We grew up a little bit. So now we are printing these hollow tubes structures with cells. And the idea is, again, we're moving towards simulating an airway. So the idea is to have air flowing in the middle, having epithelial cells exposed to air, and then other cells exposed to the medium. And of course, taking advantage at its best of microscopy, we can look at how the cells are remodeling the extracellular matrix and seeing if they are forming the tissues that they were supposed to form. So in conclusion, we opened a Pandora box because, as you notice, there are so many decisions, so many steps to be taken into consideration. And I would like to leave you with this image here in mind in terms of what's the most important decision you can make when you are playing with 3D bioprinting. It is about finding the happy balance between your application or the type of cells you have versus printability. There is no right or wrong answer. That's going to be defined completely depending on the application that you are doing. But this is the biggest challenge that we have and what probably makes this field so fun. And again, there is one path and many possibilities. And as you notice, we do have input and we have the combination of so many areas into this umbrella of tissue engineering and bioprinting. So if you like cell biology, image processing, microscopy, materials, whatever, there is space for you. Just find your niche and join us to this long journey towards finding a way to print artificial organs and tissues. So, and my email also got messed up here, but if you would like to chat or have any additional information, I'm happy to connect with you at some point. So thank you very much. And I don't hear you or I don't see you.
Here. Okay. Can you hear me, Leila? No?
Yes. Yes.
Okay, perfect. So now we start some questions. If someone have questions, comments, please. You can be coming in the front and we can do the question in Portuguese or English. It's important to speak in the microphone.
Não tem ninguém que vai reclamar do português.
Pode ficar aqui, quer ficar aqui já? Vai estar aqui à frente. Dá um oi para ele.
Oi, obrigada pela palestra. A minha dúvida sobre vascularização, que é mais complicado, seria por conta de não ter o estímulo certo ou por não conseguir imprimir ele o vaso oco, ou a célula vascularizada ela é totalmente diferente de uma célula de um tecido, que imagino que sim. Essa é a minha dúvida.
Desculpa, tá difícil de entender, tá dando eco. Fala um pouco mais longe do microfone, eu acho.
Mais longe.
Isso aí.
Aqui?
Isso aí.
Tá me ouvindo bem assim?
Aí.
Pede, por favor.
A minha dúvida... Tá dando para ouvir?
Tá.
Ok. A minha dúvida ela é sobre o tecido vascularizado, que você falou que era um dos desafios. Então, se é por conta do estímulo que é feito, né, ou se é por conta de o vaso ter que ser oco e aí na hora da impressão não tem como fazer isso, ou se é muito por conta dessa diferenciação entre um tecido e outro, então teria que ser pelo menos 2 extrusoras, eu imagino, enfim. Eu queria entender quais são as especificidades da bioimpressão de vasos com o tecido.
Não, ótima pergunta. E, bom, tem várias formas que a gente pode... Desculpa, eu não consigo falar em português alguns termos. Tem várias formas que a gente consegue contornar esse problema. Um deles, por exemplo, seria você considerar a parte de ser uma estrutura oca, sem dúvida, é uma das coisas que tem que ser tomada em consideração. Então, provavelmente, dependendo do que você está fazendo, tem algumas estratégias que você coloca, por exemplo, como se fosse agulhas dentro da estrutura que você está imprimindo, para manter aquele channel vazio. E aí, depois, você consegue colocar um segundo tipo de célula específico para vasos sanguíneos, para se desenvolverem e formar a vasculatura. Essa é uma das formas que dá para fazer isso. Mas dependendo do que você está fazendo, isso não você não consegue fazer isso. Se for uma estrutura muito pequena, você não vai conseguir fazer esse monte de channels, vamos dizer assim, no seu objeto. Então, você consegue contornar isso tentando adicionar um biomaterial que vai proporcionar o que é chamado de sprouting, ou como é que se fala, um brotamento de vasos. E aí você consegue, via bioink, fazer com que certas células formem esse network que vai depois se desenvolver numa vasculatura. Então, aí começa a complicar um pouquinho mais, porque você vai ter que ter 2 tipos de célula diferentes, você vai ter que adaptar a sua bioink para alguma coisa que vai proporcionar elas a dar esse brotamento, vamos dizer assim. E, de novo, vai depender da qual estrutura que você está tentando fazer. Respondi mais ou menos?
Respondeu sim, obrigada.
Quem mais? Você? Não? Mais perguntas? Pode ser melhor.
Oi, Leila. Eu vi você pela primeira vez na semana USP, 2020, eu acho. Bom revê-la. Então, a minha pergunta não é uma pergunta, mas eu queria que você desenvolvesse esses comentários que eu vou fazer, porque eu não entendo do assunto. É o seguinte, como que crescer um tecido se distingue de um tumor, já que as células não são organizadas de uma forma mais fisiológica, né? Mais natural. Então, como é que isso se distingue de um tumor que vai crescer? E existe uma forma certamente que não, de crescer um sistema elétrico, um sistema nervoso para guiar esse sistema que está sendo desenvolvido, essa monte de célula. Então, eu acho que são 2 complicações que eu queria que você desenvolvesse um pouco melhor nesses seus comentários. Obrigado.
Imagina. Então, essas são também perguntas muito interessantes com relação aos tumores. Na bioimpressão, a gente tenta proporcionar às células... Bom, tem 2 histórias aí. Se o seu ponto é desenvolver tumores, por exemplo, você pode seed células de tumores numa certa bioink e aí deixá-las desenvolverem para formarem um tumor. Mas em termos de prevenir que células normais fiquem como um tumor, não é tão complicado assim, porque basicamente tem muito estímulo químico acontecendo no corpo, vamos dizer assim, para fazer as células diferenciarem de normal para tumor. Então, vai um pouco além de simplesmente ter a estrutura que você coloca elas. Você vai, por exemplo, se você quer simplesmente imprimir um tecido normal, você vai ter a sua matriz, o seu substrato, vamos dizer assim, vai ter os ingredientes que o tecido normal deveria ter. Você vai colocar aquelas células lá e você pode fazer certos tratamentos para fazer com que elas se diferenciem em diferentes tipos e whatever que seja relevante para a sua pesquisa. Do ponto de vista, elas geralmente não se transformam em tumor, porque elas não têm a genetic signature se você estiver trabalhando com células normais, para se diferenciarem daquela forma. Então, se você quiser que uma célula normal vire um tumor, tem formas de fazer isso. Você pode adicionar certos químicos, você pode fazer certos tratamentos, e você pode fazer com que elas modifiquem o fenotipo e o genotipo para virarem células tumorais, por exemplo. E aí, quando isso acontece, aí sim, elas vão começar a mudar toda a estrutura ao redor delas para fazer algo que vai ficar mais semelhante ao tumor. Tem um projeto no meu laboratório que eu tenho uma aluna trabalhando justamente com imprimindo um tumor artificial. Então, ela já vai começar incluindo células normais, células tumorais, e aí a gente vai começar a brincar com a geometria do negócio. E aí você tem toda a parte de ter eu não sei em português, um necrotic core no meio, e aí você começa a colocar essas layers de células lá, e aí você vai criando o que a gente chama de microambiente, microenvironment do tumor. A outra pergunta, desculpa, eu esqueci, qual que foi?
O sistema elétrico.
Sim. Sim, eu não trabalho na área de neuro, mas tem alguns grupos trabalhando nessa área. E sim, tem algumas pessoas trabalhando com biosensors e eles tentam integrar a parte do estímulo elétrico para, por exemplo, em cardiologia e em neuro, isso acaba sendo bastante relevante. Tem um grupo, inclusive, muito interessante que eles estão tentando formar canais para guiar o desenvolvimento de neurônios e formar as conexões de uma forma mais organizada. Então, sim, estímulo elétrico, sem dúvida, é uma das coisas que pode ser incorporada, e tem alguns grupos trabalhando nisso. No meu caso, no meu grupo, a gente não trabalha com nada disso, mas é totalmente válido e tem bastante gente mexendo nessa parte.
Bom, mais perguntas? Eu queria fazer uma colocação, você sabe muito bem que não tem experiência nessa área, mas assim, olhando para as aplicações, assim, qual que é a finalidade última de você imprimir esses mini órgãos ou tecidos? Eu entendo que não seja para transplante, obviamente, mas pode ser para testar equipamentos, procedimentos, que você evita a utilização de órgãos, né? Então, nesse sentido, assim, esse é um ponto que eu queria saber, que você expor de maneira mais ampla possível, né, onde se quer chegar, né, com esses órgãos, e como que é, por exemplo, a durabilidade do tempo, quão estável é isso, e outra coisa também que a gente sempre busca a gente tenta mimetizar a função do coração, por exemplo, né? Mas muitas vezes, quando falo em bioprints, eu visualizaria como mimetizar a estrutura, sabe, a estrutura do osso, a estrutura volar. Isso é um problema, isso é uma tendência. Se quer fazer isso, mas eu queria saber mais da sua opinião em relação a esses 3 pontos.
Então, isso aí bom, o que a gente fala o mundo ideal, o futuro ideal a gente seria capaz de imprimir full organs para ser transplantado, mas isso ainda está bastante longe de acontecer. Porém, uma das aplicações que é bem imediata e acaba tendo bastante impacto por exemplo, só para ilustrar, usar esses tecidos artificiais para testar medicações. Então, em vez de você usar, que nem eu mostrei no começo, a 2D cell culture, que é a célula no Petri dish, que é muito simples e não necessariamente captura todos os comportamentos que você poderia ter, a alternativa geralmente é usar animais. Animais está no outro lado do espectro, já é um negócio muito complexo, você não necessariamente tem controle exatamente do que está acontecendo ali. Então, essa parte de tecidos bioimpressos acaba sendo um negócio que você consegue posicionar no meio dos 2 mundos. Então, você consegue ter estruturas que você pode fazer elas tão simples ou tão complicadas quanto você queira, e controlar um pouquinho mais os estímulos, controlar a composição, o tamanho, o tipo de célula, por aí vai. Então, tested medication é um impacto que já está acontecendo bastante. Outro é relacionado à medicina personalizada. Então, por exemplo, você poderia desenvolver um tecido artificial básico sei lá, de algum tecido, e aí você consegue pegar células de pessoas, de pacientes, colocar nessa matriz, nessa estrutura, deixá-las crescerem, e aí vamos supor, no caso de uma quimioterapia, que geralmente tem várias opções. Qual das opções da quimioterapia seria a mais eficiente para atacar o tumor daquela pessoa especificamente? Então, você cresce um tumorzinho, um mini tumor daquela pessoa, testa as diferentes drogas e vê qual que poderia ter a maior chance de matar aquelas células. Então, nessa área de medicina personalizada também é uma que acaba sendo beneficiada dessa tecnologia de impressão 3D. Tem muita gente trabalhando também com queimaduras ou, eu não sei o nome em português, feridas chronic wounds, papéis caras, essas coisas. Então, por exemplo, você pode criar como se fosse um band-aid biológico, vamos dizer assim, que aí você coloca na pele, você acaba promovendo certas células, certas coisas acontecerem para ajudar a fechar aquela ferida e por aí vai. Qualquer outra parte?
Em relação à durabilidade disso, se você consegue reproduzir o colágeno, é uma estrutura durável no tempo, assim, né? Se é isso mesmo que você consegue depois da impressão.
Geralmente, de novo, vai depender do qual que é o seu objetivo, né? Mas geralmente você pode manter, por exemplo, a gente fez um estudo em relação a pulmões, que a gente deixou as células, ou a estrutura toda crescendo por 30 dias. Então, assim, geralmente o que acontece depende do que você está fazendo em termos de desenvolver órgãos para transplante, por aí vai. Tecnicamente, sim, a gente está usando os mesmos building blocks que a gente tem nos tecidos normais. Então, não é para ter nenhum problema em termos de durabilidade. No laboratório, para essas aplicações mais básicas, vamos dizer assim, teste de medication, de medicina personalizada, geralmente você não precisa se preocupar tanto com um long-term culture, né? Porque você quer descobrir as coisas, sei lá, em coisas de semanas, 2 semanas, 10 dias. Então, assim, em termos de durabilidade, esse não é o maior problema. O maior problema está sendo, por exemplo, vascularização, a definição da estrutura mesmo. Tem outras coisas que são mais críticas.
Mais questões? Não? Bom, então a gente pode encerrar a sessão, né? Leila, muito obrigado de novo pela nossa bela apresentação didática, boas imagens, foi impressionante. E obrigado.
Até mais.
Obrigado, Leila.
Tchau.
Bom, temos algum aviso